y'all got any questions? And my name is Nadia. I'm second year position. So let's start. You guys, what to begin with?
I mean, off the top of my head, but I'm not for like the exam. It doesn't have like a solution for it, so.
You want to go over that?
Yeah.
You okay?
Thank you. What are the solutions we can just look at? Check.
Yeah. All right.
So this way,
Okay, so give me the problem. First one, you have the problem.
Exam one.
from, I know, but let's, that's true.
Oh, I don't think it's that. It's just, it's that exam one when I was back home.
Okay, I'm going to be writing. So that's problem number one. Three charges are arranged and depicted below. And we have this. Very good. Sorry, it's not right. So, here's one. So, Q1 is 40 centimeters from the other two charts. Sorry, Q2 is 40 centimeters from. So, look at 40. The charge on Q1 is 39 seconds. 3 seconds. The charge on Q2 and the charge on Q3 Number one, how the force is acting on charge Q2 in the diagram below. Be sure to represent the approximate relative magnitudes of the forces in the diagram. So, okay, let's start with one step. Q1 is positive, Q2 is negative, and Q3. So, let's first consider the pair Q1 and Q3. How does Q1 pair? What is the direction of the force?
On Q3,
Yes, from Q1 and Q2.
they're gonna be going like this. What is that, right?
So, yeah, the force exerted from Q3 from Q1 is towards the opposite behind. So, like that. Right? What's the force exerted by Q2 and Q3? What's the direction? Yep.
Out. Because the local view.
Yeah, so away from it. So I connect. We're doing exam 1, 7, 17, 20, 23. About the outcome.
Yeah, they're not sure.
What? Oh, okay. You found it?
Yeah.
Okay. So,
versus
Okay, let's start with this one. How is the Coulomb's force defined to
force.
yeah.
How the two charges with that one?
K and
Oh, yeah,
Q1
yeah.
Q2 over R squared. Where Q1 and Q2 are the charges and that R refers to the distance between. So in our case, the R charges are different. So right now looking at the picture, it's really hard to say which line is really clear. Well, because, I mean, you know that the distance between Q2 and Q3 is 40, and the distance between Q1 and Q3 is 48 squared, 670. So the distance is greater, but the charges are different, the magnitude of the charges are different, so it is, I mean, approximate relative magnitude. So
Is that the first question? Is which one
Yeah.
is magnitude is greater?
it says be sure to represent the approximate relative magnitudes of the forces of the diagram. So maybe he meant not, I mean, draw one explicitly very, not one of force. So I would say they're roughly the same, very roughly. Let's calculate. Okay, let's see. E shows calculate the net force acting on Q3. So there are the two forces acting on Q3. We know them, right? So F net is F1 it's hard. I mean, you can draw a diagram and how you add vectors. In here, it's convenient to look at the area. So that would be F net. But it's easier to do with these by projecting them from F and F1. So let's first project on what's the projection of F3? F3 lies entirely in the x direction and points to the positive x direction. So its projection is F3. F1 is going in the negative x direction. So it will be minus the magnitude of F13 times it's in order to say that we say the diagram. So what's the x component of F13? In this case, doesn't really matter, but yeah, total. So what's the F23? F23 is so K times Q2, Q3 over, let's say that this is 40 is R. So the difference between Q1 and Q3 is R for convenience. So over R squared minus K Q1 over R squared, no R. What's the distance connecting one space? R. Now, note with the sign. I already took into consideration the sign of the chart, right? When I was drawing the forces. So in this case, I need magnitudes of because I already considered the negatives. Yes.
So if you wanted to, could you just put in like the exact values of the signs and then what would the next what do you think? Like put in like the charges by themselves and just add them. Like charges with a negative sign.
What do you mean?
Like so we're finding the net, so that's F13, and then the second one's F23. If we just did F13 plus F23 and then didn't take into consideration the signs yet, and then put in the signs with the charges.
It's confusing. I think this is a little confusing. When you are done considering the direction, don't mess with direction anymore and line it just to get up to the You can calculate this because you know it. Right? I mean, I won't go to calculate.
Is that a minus or?
No. It is. Right. But yeah, that's your final goal. For just the X component of the network. For Y component, the Y component of F23 is 0, right? Because it's entirely in the X direction. So for that, for Y, you just have F net Y is equal to the projection of F13 on Y is positive, right? This one is like this. What's the max? F13 times what? This is the example without the answer for every definition of problem number one. So F net Y is equal to F net Y.
Cosine of pi over 4.
Cosine?
Cosine.
Right. Which is equal to K times again the absolute value because I already considered the sign. So U1, U3, squared times 10 times. Okay. So how do you find the magnitude of the network? We now have the S and Y components, right? So imagine this is our F net. This is net. How do you find the magnitude of F? So F net from Pythagorean theorem, right? F net squared is F net X squared plus F net Y. You have F net X right here and F net Y there. Now part 3. In what general direction would an electron initially travel? Place 5 centimeters directly below. In what general direction would an electron travel? It's place 5 centimeters below. So somewhere, well, it's hard to do scale. Let's say it's in the right. So to determine the direction, we need to consider what direction is that coming from, right? So how many forces do we have at right? From 1 to 2 and 3. What's the direction of force of that 3 is very what direction? Yeah, straight down. Okay. What's the direction of Q2 1 along the line connecting the target, right? Oh wait. What direction of F1? Again, along the line connecting the target. So that's F1, right? I'm not sure. He's asking in what general direction, so I think we have to go. But you can also go. Why do we need to calculate that? We need to calculate the net. Net is the vector calculus. Net is the vector calculus over. So your electron, if you go in the direction that it would of the net. Right? Yeah, you have to find the net first. And try to draw a good picture. Probably this is the net force. This is not very good. And
down to the right, those the negatives are getting closer. That part of that is much greater than the positive. We just have to let the positives go.
so that you so now you will do this one as well. So I would say that but I would say this is legit. This is good enough for the good of it. And go. Okay, let me review it. So, the 4060 charges that are, say, time of the charge are repulsive. The sign of the charges are opposite, they are right? Force is proportional to both of the charges that are in the same direction. And inverse is proportional to the square of the square of the equation. Yep. Now, let's go here. Change the an infinite sheet of charge. This is a surface charge that is bigger than the point charge of 5 microvolts located 4 centimeters to the left as a surface. So that's how this goes. This is simple. Either be like the point charge minus 5 microvolts located 4 centimeters to the left. So, and this is determine the electric field at a point located 5 centimeters to the right of the control. If the light represents the light is not to both axes, charge at the point of interest and the phase part. Okay, determine the electric field at a point located 5 centimeters to the right of the control. So at this point, so the field at A, like, is this field what's the direction of the field at point B? To the left. Okay. So the field at A is simply equal to D plane minus E. Where this bullshit. I'm taking it. Okay. This is what. So what? You know what? You're doing. It's the one that hasn't missed. Common number. So how do you determine the field by the plane? What's the question? Do you have it in your? Good. Notice that field of the infinite plane is not dependent on the position from the sheet, right? So it can be like okay, 100,000 miles away from the sheet and the field is the same. So if you of the point charge. Where R from the Q to A. Yeah. Right? What's the Q of? Q of the good. Yep. So now E is going to be sigma over Q epsilon naught minus A Q over R Q A, which is 9.8. Notice that this is the absolute value because I consider the direction here as a type. So my field is going to forward, or my left. So I'm taking that later. Okay? Good. So yeah, that's it for that.
If signal was negative, you take absolute value negative,
This signal was negative. Let's say now the signal is negative. What will be the direction of the plane? Yeah. So my field here at A would be the magnitude of it would be equally plus and it will be in the negative x direction. Usually what I do on the exams, I calculate it somehow like this and then say that it's a game or not. I don't really like messing up the time. I would project it first and then determine. I just pick the positive x direction that way, right? And I project. So that's the formula. Finally. That's good, right? I can go to the next. Ask the question. Number. Consider the same point charge at the center of two different spherical surfaces, having a radius 3 times as big as the one shown below. So we have this here, this surface. I think both things, but I'm not sure. pair of point charges inside it? It's not in the equation, but let's say that this here is the radius r small, and this one is the radius r big. So these are little r. And here is the inside of this. Compare the electric flux. So each. So what's flux? How do you do it? Right? That's your formula for flux. Okay. So what? E? What's the field? Yeah, good question. How did they determine the field force of the point charge? Just the KQ over R. Where R is the distance between the charge and the point of it. Right? Good. So, the field of the point charge is pointing radially outward, right? And since our field within total feet of the unfold. So the field at the distance, at the equal distance from the point charge, here, it's the same, right? So I can pull the field out of the equation. Now the dot product, we should consider the dot product. The dot product refers in math, right? So the dot product of the two vectors is absolute value in the first, times absolute value in the second, times the total time of the input. So in this case, your field is to be perpendicular to the surface, right? So you might think cosine 90 as 0, so I should have 0 plus. But the thing is that for, okay, area, which is D8 refers to. Area is generally a scalar, but once you're using the vector form of the area, it refers to the norm. Right? So in this case, we know that for a sphere or a circle, this line here is perpendicular. So our field is perpendicular to the surface. So it's parallel to the normal of the surface. That's why we have cosine 90. Sorry, cosine 0. So our flux becomes simply E point 8. Right? That's the point of the reason. So the flux in this case, what's the field? It's A times E, right? Over R squared, right? Times 8. What's the area of the R squared? I will find it. That's our first one. Flux for this surface. Okay? Help me out. A times You will go. Let's first start with the big R. R squared times 4 times big R. Right? This can be simplified. A times 2 times 4. Okay? A times 2. So it looks like our
Even though it's like radius. This actually makes perfect sense.
the version of block, like the number of the field line conversion for the radius, which starts to change because of the same charge. Right? So if they have a similar amount of electric field line piercing this surface or this surface or any other surface, they'll have the same. It can be.
Yes.
Yes. Okay, so we, for E, let's first thing for the field. Field is, like I said, in the formula, is determined by the formula K times P over R squared, where R refers to the distance between the charge and the point measured, which is anywhere on the surface, right? And we want the flux of this same surface, so that's why R. In this case, R is a bit better. I will go to the So in this problem, a solid sphere of radius r has a total charge Q distributed evenly throughout its volume. What fraction of the total charge is located inside the radius r over 2? So I will look at R. And we have charge Q. Evenly distributed. We need to find what fraction of the total charge is located inside the radius r over 2. So if it's evenly distributed, we can something that volume charge density rho, right? Because it's evenly distributed, we have a certain amount of charge per unit volume. Think of it like a regular rho, like a regular thing. So your density times volume equals to mass, right? So in here, it's the same concept where rho is the charge density of the mass. Similar concept. So rho is your volume charge. So what would be Q? Q is the total charge. How do you write Q using rho? So total Q, like I said, think of it like is equal to rho times V, where big V is the volume, the total. Okay. What's the volume? It's 4, 5, R. this little here inside has a charge Q. Little here. So the little Q is again wall times little v. Where little v is the volume of the small sphere. So that's it's written here, right? And so it rolls and circles are over 8. Okay. Check that. So now we want the fraction of the total. We want the fraction of the total charge that's located inside the little. So we want Q over Q. Small, tiny little Q, and big Q. That is 9 R2 whole over 6. No, it's 4 third 5 R2 and 4. Now this is 4 5 R2 this is the 1. Yes, it's the same. This is just the same part, I mean, the inner part. Because it is the part, uniformly distributed over the big circle. Rod here is not here. Same. Okay. Good. And there is the answer to us like that. That's good. Does it make sense? Where? Oh. That's good there. You're good? I can go to the next problem. Good. Next problem is problem number 1. A burning charge Q1 is located at the center of the fixed conducting sphere. So, you know what? I'll get to sign up. Like short-term charge located at the center of a fixed conduction sphere. conducting movement. We take conduction field in the radius A and all the radius B. A. Conducting vertical shell with net charge Q2. And Q2 is net. What is the electric field location P, 11 centimeters above the plate charge? So, in this case, we need field, right? For part A. What's the convenient way to find field without electrical resistance? Yeah, use the calculus. How do you write without integral? Is equal to what? So when we use Gauss's law, it's convenient to be without surface. So what do you think is without surface? Good. I agree with you. So down, the green one is so down. What's the radius of the our dot here? What?
The radius of the dust.
So yeah, the distance between Q and P, which is okay. So now go back to this. So everywhere it's here, due to the symmetry, everywhere it's here. And I like to field lines are perpendicular to our Gaussian center. Something all of these. Oh, it will be right because our over under equilibrium and from both surfaces and nature. So you're right. Fine. Okay. That's where we are integral behind the equal to rules over epsilon naught. So since B is constant and the integral of dA is just the area of the Gaussian surface, which is what? Y1 squared? A is the Gaussian. Okay, let's think. We want block through because you see that this block, right? We want block through this sphere. Yeah. I noted in the yeah, that's another thing. I'm sorry, for some of these questions. Let's do the next one. Now, about the Q enclosed, what's the charge enclosed are, yeah, the green also. Yes. You haven't worked anywhere today, everything. Yes. Yes. We are, okay, let's think about it this way. We are looking for the field at this point, right? This is why A is for green Gaussian. So in Gaussian form, A refers to the area of the Gaussian surface. Okay. So from this equation, we can pull out E. E is A1 equals E2. No, I'm not writing any output values here. So this one will be actually negative. Divided by 5 epsilon naught r. We use, oh wait, what's the E field? Yeah, this one. That's it. That's it. Where are you?
Good question. I was really figure out about this before I did, but why is that why is that, or why exactly is it constant?
Why field is
Yeah.
field is constant over the Gaussian surface? Okay, think about
Okay,
it.
so it's not changing from one to the other.
At every point of the surface, yes, the magnitude of it is the same. And it's always perpendicular to the surface. Like I mentioned before, don't be, I mean, if your field is perpendicular to the surface, dA, the vector dA, refers to the normal. That's why if your field is perpendicular to the surface, it's better off normal. That's why the dot product actually valued as so your code, because your code and zero. Good. Ask you a question. What is the charge density of a signal in the inner surface of the conductance particle cell?
Before you move on,
Okay.
you said that the one of the charges is negative. Is that including the charge?
Yes. Cupid. I don't care, like, when I'm writing out,
Go on.
I don't care whether it's positive or negative, because I'm not considering the field. I'm with the convenient tool where I don't have to consider the magnitude or integration or anything. I'm just summing two equals. You just add Q1 column the negative. Not the negative. So it will be, yeah, so this one will be positive and this one will be negative. So you're summing positive and negative values. Okay?
So that is doing is just, like, just
For example, okay, here. This is the charge. We already, it's probably, so this is the infinite charge plane. The plane is positively charged. And it has a minus q. So, and we were trying to find the field of point A vector. So when I was, there are two fields, two sources of field in this situation. One is the plane and the other one is the charge. So in here, I explicitly consider the direction of the field. So this is E from the plane, and this is E from the field. I personally like this stuff because I like to consider. But then doctrine, you do not explicitly consider the directions of the pyramid. So, you did not say that for this positive charge, the field would be moving this way and this way, gradually outward. And for the negative charge, it's a little complicated here because you'll have negative charge, it's further in the problem. You have negative charge on this field, which is positive. And whatever is left out on the outside is. So, I did not write superposition, so I did not consider complement and direction. I'm just taking the charge in place. And then the force. Let's look for the What's the charge density signal on the inner surface of the conducting surface? Do you have any idea? What is that?
Charge of DNA.
Yeah. No, since it is a conductor, our entire charges distribution will be on the surface, on the inner and the outer.
So that's what we're talking.
Yeah, because according to the division of the normal charge. The thing is that in conductors, you have three charge carriers moving around, right? So as long as there is field in the conductor, there will be continuous field. That's why the field inside the conductor. So that's why it looks like so that this is the usually for the conductors are just given the signal as for escalators. What's the charge? What kind of charge do you have in the inner circle? How does it? What? No. Wait. What is the inner surface of the positive for energy? Yeah, this inner charge here produces the field right now outward. This, that, everything. Right? And this conductor is responding to the field. So since the field is pointing upward, these electrons are responding to this. So this one, even if our conductor had looks like it's usually what's called an inner surface.
So the outer surface is conducting.
Ours,
Yeah, surface is conducting.
field away from it, radial outward. And the electrons in the conductor are responding to the field, right? So, like you already said, it's inside the conductor. It's zero. So, how would you approach the problem? What do you have ideas what you can do?
So just a line.
You're trying to find that question. So sorry. There no what? Can you write the question? Pick a document. Where will be a good document? A? A will be a good document. I want to take a document here. I mean, I don't care if my R of the Gaussian surface is between A and B. So, using the Gaussian law, we have A is equal to Q enclosed over epsilon naught inside the conductor. I field is zero, so this whole thing goes to zero. That's why my Q enclosed over epsilon naught should be zero. Well, epsilon naught is a constant, we know. So, apparently the Q enclosed is the charge on the inner surface plus this little, that's how it is. I mean, good. So it's like it's good. So, Q8, right? Q8 is minus 2. So what's your sigma now? Sigma 8. Sigma 8 is Q8 over, what's the area? This? Where that little Q is. Because this is there. So my Q enclosed is Q plus Q8 equals this. But what's the electric potential of the outer surface of the conducting shell? Assuming that the potential is zero, is zero at infinity. Create potential of the outer surface. Oh no, potential. What's your equation? Oh, can I go to the initial before? Your concept. Oh, that's actually A, B. We don't need C anymore. what's your formula for potential? What's F? Reverse. Okay. Here, so refers to the distance. In the center to the point. That's potential. How? From A to point B. A. In problems like this, we like go in from infinity. So let's say we have point A here. That's G. So the A is determined as the integral from infinity to A of T W. But this how do you how we find the code? So yeah, you're right. For usually when we're asked to find the potential, you're setting up this equation and then you need another equation where E comes from. That's usually how it's most convenient. So Gauss's law, we already solved it. This right one. E dot E A is equal to Q enclosed over epsilon. In this case, in this case, E times dA, sorry, E times A is equal to Q enclosed over epsilon. What Q enclosed? So 1 plus 2, right? That's over there. Over where R is the distance from the center for the point of reference. We're going to write it as R for now because we're going to put the limits of integration into our equation. So we'll take this and use it here. So that would be 1 plus 2 is the constant. That's why we can pull it out of the integral. 4 y epsilon not just constant. We can pull it out of the integral. So in the integral, we'll have 1 over r squared. The r. Notice that I'm changing the L to the R because L. No, it's not at all. I'm just using this R notation because R here refers to that potential. So the letter itself doesn't really matter. As long as you're referring to the same thing, the same distance. You can call it ever to ever if you want. I mean, it's a notation. What are my limits for? So infinity. Do you know what? Oh, this part is. Oh, sorry. I have 1 over R. That's what it You know how to integrate, right? How you solve it in or should it Okay, so if I don't have this explain, get 1 plus 2 over 4 by epsilon naught times 1 over negative negative 1 over r, and my limit back comes inside. I forgot one important thing. Don't forget because it will ruin it. This is negative. This one's negative. This is negative. It's positive. So that will be eventually 2 1 plus 2 over 4 times epsilon naught. There's your potential. Okay? This is the potential at A if we consider that the potential at infinity is 0. Notice that potential itself is not an absolute value, it's like a potential energy. You can take the 0 wherever you want, and that would change your potentials everywhere. Like, think about it as potential energy. We can choose, if I put this marker on the table and choose this as my 0 potential energy, that will be 1. I will have one result considering the motion of this marker. But if I put it on the floor, for example, and choose this as my 0, that will be changing, like, right? Change my value. So I was just making sure that you understand that this is not an absolute value that will be the same everywhere. No, if you took a different 0, you have a different thing. But we chose 0 to be infinity. So, yeah, and he pointed out in the problem. You're good. Just, I mean, you don't have to think about it during the problem. It may be confusing, but just understand it at the back of your head. If you put a 0 somewhere else. Then. Yeah, you can. It will be complicated though. Yeah, you're able to go from 0 to 8 and to 8, considering those bits. So, I mean, the problem is asking, pick the 0 then finish. So we go from yes, the focus is infinity. Infinity. That was the trick. Okay, that was part B. Part B, because B. What's the electric field inside the conducting shell? Oh, that one is. What's the electric field inside the conducting shell? Good. That was easy. What is the electric potential at the inner surface of the shell? Oh man. Inner surface. Remember our selection concept. Okay, I'll draw the picture. We need potential at the inner surface. So that wait, let's go going M. However, when you're in this problem like this, you want to go step by step because the dependence of the field on the distance between the distance to the center and the point of interest will be different. Yeah, the dependence and the formula are different. Right? So, you want to go from denominator and you want to split this integral. Okay? And if you have more surfaces, if you, for example, have an interior or another interior, you want to do another. So you want to go step at a time. Yeah, so you consider like air, metal, air. Okay. So I could take a minus out. Okay. That's the integral. And then create industrial. No? Because they're minus. That's zero. Right? We found this already on the previous page. So you can go back in your notes and see. What's this one? One? Ink inside the conductive strip. So, our answer is just like in the previous thing.
That's
What?
very sorry. This is just kind of
Oh, yeah, that's the start.
when we went through it.
Oh, wait. And I go, sorry, that's, I'm sorry. Sorry about that. Split 8. You're right. I'm sorry about this.
Who said that?
Like that. Now, what does it tell you? Remember here it said 0.8? So potential is 0.8 and statement potential is 0.7. So, remember in your lecture, I think you said the surface of the metal ever. Okay. We're done.
What is the one from A? Sorry, this is really
B to A. See, the integral from B to A of E dot dl here, no, because field inside the conductor. Okay? That's why the integral is here.
I got that.
That's why this is 0 and this is already solved. These are questions with one solution. So the potential at A is the same potential at M. So I think we're done with the worst problem and the because we have to apply both jobs and the okay, number 6. Two charges are equal in magnitude and opposite in size. When the equal distances from 1 to 2. So that's number 6. Sorry. Yeah. We have 1. charge is equal in magnitude, it's opposite of sign. So let's say that Q I place the equilibrium system. I place the equilibrium system point Q extra. So we have so that's correct. Equilibrium. So system this so not P that. If a third charge. Oh, that's point Q. If a third charge is added to the equilibrium and placed at point Q, how does the electric potential energy of the charge collection change? But let's stop it. What do you mean? We need, okay, consider no charge here. We had no charge in the beginning. We had some potential energy. If we put a P here, how will potential energy change? Okay? So, what's the potential energy to begin with? Potential energy. What's the purpose of potential energy? I don't know what's potential energy. So, K and Q let's say this distance is R. Right? No more explosion of potential. Estimate. What's our final? If we introduce the charge, they consider all there, right? Okay. So, what's the, if this pair doesn't change, right? So we still have A times Q times minus Q over R. What? Now, this pair. Q, wait, K times Q times big Q over T. What? Times Q times Q over T times T. This plus that is 0. Right? So, my potential energy in the final case is Q times minus Q over R. It was as it is as it was, not change.
But if you ultimately say, they're both,
If they're both positive, then those are positive. If they're both negative, then you have a change too. Because these two items will cancel out nicely. When, I don't know why I wrote. Oh, because of energy. You like you? Correct. I thought see, that's my final formula. That's my this because of this Q and this minus Q, in the sum they would give us 0 no matter what Q is. The big one. Okay? Because they're exactly the same except for this one. Correct sign. In fact, you can play this Q at any point along the line, along the line that is passing through the center. At any point, you can place Q moves. Right? Everybody understand? For the fourth charge, does he add it to this system without changing the potential energy? And if so, where? Putting another charge in infinity is not enough. You can, yeah, you can put it. You can put this in like, oh no, never mind. You have to consider actually this. Never mind what this is.
So that would be exactly the same.
What?
Like that, and it's something.
Oh, you mean put the Q here, now get a portion?
Yeah. That'd be great.
Well, why would you do it? Because you need to consider everywhere. So you're not only considering this and this, but also this and this. This. Negative Q. But your final would be then what? The rest are symmetric. This is true. I don't think so. No. No, in fact, he is not doing like that. Wait. No. That's not right. I think yes. Because this can be with, okay, if we put that other unit on this line, it will change everything. But if we pick Q1, that would be my Q1. That would be my Q2. And this is well, I need such a combination of Q1, Q2, and Q3 and Q1 so that my potential energy doesn't change. So this whole addition that I just put should be so I think it's a good. So I don't think we can solve it, but I would say, yeah. You can try everything. Well, what I'm saying, it can be equal to, I think, good collection we want to do food. Because our chart doesn't have to be equal to whichever of these, like any of those charts that are over and we want these. So I would say let's consider this. Let's say here. So the fact that it's here didn't change anything for those two. But then you have to consider all pairs. So there is also this pair which is an additional pair.
The only thing I'm confused on is if you move it to the left a little bit, don't you still have that pair? Like if you move it to the left, so where you move Q1 to the left?
Here?
Yeah, so you still have that pair Q1, Q. So we need to get
These ones are this one, this and this pair, those two goes. So would they cancel the third interaction? Technically, okay. Well, you almost did.
Yeah. So this is
I know it's not a very good explanation, but anyway, I would say this one. I don't. In another one of your practices that was just straightforward, and that was very good. Anyway, can I go to question number 7? Okay. What? Not me. Hopefully, a 9-volt battery is hooked up to the circuit to fix it below. The values of the capacitors 1, 2, 3, 4, and 5 are given. That's your step. Thank you. That's what that is. This one looks like something more for film. I think I saw this problem before. What is the equivalent capacitance of the entire circuit? So our first equivalent is these ones are evidently featured, so we can rewrite the circuit in the following way. So, P23 is what? Which is complete, which is what? Because it's 3. What can we now see for sure? Which one does evidently? 4 and 2, 3 are evidently internal. Why have we those to this? Then these 3 are unique. You can finish this one, right? To find the total. Not. Whether you can find the total capacitance from now on. These 3 are in series with each other and we know each. So, you don't want to multiply them here. Yeah, so you find each. Yeah, because all get out. No, you are given, I just gave you that. You are given C1, C2, C3, C4, and C5. It's there. Right. Yeah, if I am writing, what's the charge of C1? What? Let's look at this one. This one. These three capacitors are in series, right? So their voltages are summing up to the voltage of the battery. Think about resistors similarly. the voltage drop at each resistor adds to the total voltage on the battery, right? Because the current through each of the resistor is the same. Technically, you don't have current here.
The current thing involved in the series charge.
Technically, you don't have the current here. You have. Let's think of electrons. What?
As for resistors, the current is the same phase circuit, so the capacitor, the charge is the same, right?
Yes. If they're in series, the charge is
Yeah.
on each of these.
So we can just find the
Total capacitor that you just did, and so the Q1.
total would be the charge on C1.
I got it.
Use the motor of that way. Use the motor of that way.
Yes. What's the electric potential delta E across C4? We found here that Q total is equal to Q1 is equal to Q1 is equal to Q5 is equal to C total, which we found D battery, which we know. So, if we know Q on 2, 3, 4, and their capacitance, their total capacitance, we can find the voltage of C, sorry, on C2.
Like on C4, just C4.
Okay.
We charge on C4 would be the capacitor at C4.
Let me go step by step. So, you know Q234, because we just calculated C total, and we know the D battery, so we can calculate. So, what's E234? It's Q234 over C. So, we can find the voltage. And then we can see that voltage on 2 and 3 is the voltage on C2 is the same as voltage on C4 because there is in parallel C2. Normally, potential if we were solving an exam together, anyway, do you have any other questions about the problem that I did?
The problem I think we're going to
Yes. Which part?
the third part, because that's the point charge, both the potential difference and A will just be B and CO, right, from B to infinity. If that thing isn't a point charge, but it was a solid insulator, then there will be another thing that will be added, right?
Yeah, if you had You want potential here, right?
Yeah.
So here you have to go from infinity to C.
No, C is in
What?
What is C? B is the outer surface of the conductor, and A is the inner surface of the conductor, but also the outer surface of the
Say it again.
So C is everything.
Say it again.
Like I'm saying that the insulator is inside the conductor and it's going, and C is that
So you're saying this is the insulator,
yeah.
and this is the end for both insulator and conductor,
Yeah.
like this.
Yeah.
Oh, and then the conductor goes to C.
No, then what's the charge that one thing that it is that what's the electric or what's the electric potential and that will be used for
The electric potential in this in here
yeah, but
it will be the same as here.
no, but what is that thing not like a point inside it's not a point charge that's not even
Yeah, that's what I'm saying. Your metal is equipotential.
so
So
would it that would also be the outer surface of the insulator? The outer surface of the insulator can be the outer surface.
Because I showed him the problem with the food, and they want the circle and the circle. He's like, oh, that didn't work. We're gonna set up with that one guy. Read a quiz on like circle, and then there's zero charge at this one point, and then within this other circle. Not parallel. But it was an insulator.
Inside a charged sphere, and the smaller sphere has no charge.
Yeah. I know, the whole thing was an insulator.
Smaller hollow sphere.
No one got it. That was a question back.
oh yeah, sorry. I don't want that. Yeah.
Yeah, this is probably. Yeah. You export that?
I don't like.
Give it to you.
The next one, three.
The California end up too, right?
Yeah.
Yeah.
You gotta do that, right?
Yeah, but I didn't buy it.
Nah, I'm still gonna buy it.
Wait, I need to take
Oh wait. Oh, you wanted to take a picture?
this.
Okay.
Yeah, I just like.
Can you file? Yeah.
Say that.
Export. I don't want the red station like that.
Sure.
Wait, make sure everything's on the slide, the looking format's right.
What? Yeah, it's 11 pages, it says.
I don't know.
Okay. What?
Sorry, I'm really good.
Let's try.
Print that out. Oh, where's the posture? Where's the computer? Inside.
What?
I think it's on, there's none of the, it didn't save.